Okay, so we're starting Unit 4, and we're going to start by talking about what a derivative can do for us graphically. We're going to talk about relative maxes and mins, absolute maxes and mins, extreme values, critical numbers, and a candidate's test. So that's what we're doing today. All right, extrema on an interval. The extreme value theorem, global versus local extrema, and critical points. The maximum and minimum values of a function are called extreme values or extrema of a function. The process to find them is referred to as optimization. You want to optimize your graph, find its max or its min. There will be times when we will want to find the max and the min for x on the entire domain, and other times when it's on a particular interval. In this lesson, we're going to learn how to use calculus to find extrema rather than using a calculator, like to graph it and just use that wonderful button max and min. So, hold on one second. Okay. A definition of an absolute or a global extrema. So an absolute extrema is the ultimate max or the ultimate min. So if f is a function on an interval I and y equals f of c is the absolute or global, most of the time you hear the word absolute, maximum on this interval, if and only if f of c is greater than the entire function f of x for all x's in I. Now, this is just fancy math talk for common sense. If it's a max, then absolutely the y value, which is what that is, at c has got to be greater than the whole function. And then I am a minimum if the y value at that c is smaller than the whole function. So we would say that the max is whatever the y value is, and it occurs at whatever the x value is. And then the same thing for the min. Okay? So the y value is the max or the min, and the x value is where it happens. Okay? The graph of y equals h of x is shown below. Determine the extrema of h of x on the interval a to f. All right, this looks like a really fun roller coaster. So we're going from a to f, and I want to talk about the extrema. Okay, now we have absolute, but then we also have relative. Now the absolute is the end all be all highest and lowest points. So right here is an absolute max. It occurs at, well, it is, sorry, hold on. The max is f of e, because that's the y value, and it occurs at x equals e. Okay. This is the absolute minimum. It occurs at the y value is f of d, so that is the min, the minimum value, that is the y value, and it occurs at x equals d. So those are your absolute maxes and mins because that is the highest point and the lowest point. However, there are other maxes and mins, not the absolute, but we call them relative. So this one right here is a relative max. It's kind of like saying Pilot Mountain is a relative max. Sartown Mountain, Hanging Rock, they're all relative max. Now, they have nothing on the Blue Ridge Parkway, but for our general area, those are high peaks. So I'm not talking about the absolute. When you're talking about relative, it's just, hey, it's taller than most things around here. And that's what this at point C is. So the relative max is f of c, because that is the y value, and it occurs at x equals c. And then this little guy, yes, it is a cusp, so it is not differentiable here, but it is still a relative min. It is at f of b, or it is f of b, and it happens at x equals b. Okay, now here's something that's really important. Relative maxes and mins cannot happen at endpoints. Relative maxes and mins cannot happen at endpoints. And when we flip the page, we're going to talk a little bit more about that. And we'll write that down in just a second, so just hang tight. Absolute maxes and mins can occur at endpoints. So since our endpoints at A and F are not absolute maxes and mins, they don't get any attention. Endpoints are either absolute or we don't care about them. All right, defining relative and absolute extrema of a function. A local or a relative extrema, like Pilot Mountain or Sartown or Hanging Rock, are y values on the graph of a function where the function changes from increasing to decreasing or from decreasing to increasing, because that is going to cause the hump. Now, you should be having flashbacks to Unit 3. Well, wait a minute. I know how to tell based on the derivative whether the original function changes from increasing or decreasing. If the derivative is positive, the derivative goes negative, and all that's going to come into play here in a second. Absolute or global, again, we're going to stick with the word absolute, the highest or lowest y value on the graph of a function or on a specified domain of a function. Again, absolutes can happen at endpoints, relatives cannot. Okay. If there is an open, all right, so we're talking about relative or local extrema. If there is an open interval, open meaning I'm not including the endpoints, containing C, on which f of c is a max, then f of c is called a relative max. If there's an open interval, again, no endpoints, containing C, on which f of c is a min, then f of c is called a relative min. So you need to be very fluent in relative max and mins and absolute max and mins. Absolute is the end all be all for the life of that function or for the life of that interval. And absolute means, relative means I could have more than one. Like Pilot Mountain, Sartown, and Hanging Rock are all relative maxes. Noteworthy thoughts. When we say an open interval containing C, we mean that we can find some interval from A to B, not including the endpoints. C will be contained somewhere inside the interval and will not be either of the endpoints. I feel like this is beating a dead horse. A relative extrema, relative, is slightly different than the absolute extrema. All that's necessary for a point to be a relative max or a min is for that point to be a max or a min for all the x's that are around it. There can be smaller or larger values of the function at another location, like the Blue Ridge Parkway, but relative to x equals c, f of c is smaller or larger than all of the function values in the neighborhood of c. So in Surrey and Stokes County, Pilot, Hanging Rock, and Sartown are relative maxes. Okay. In many cases, we will be asked to analyze both open and closed interval functions. So here we go. Consider the graph of y equals g of x shown to the right. Okay, let's look at g of x. Okay, I see that it continues to the right and to the left forever. I see that it is a degree 4. It will forever be going up, but it will not forever be going down. Okay, so I see an absolute min, I see a relative min, and I see a relative max. This function will not have an absolute max because it never stops increasing. Now, you change the interval, then it's a different story. But if I'm looking at the entire life of this function, then I see an absolute min, a relative min, and a relative max. Okay, it says state the relative extrema. Okay, so relative extrema, I'm going to say there's a relative max is 2 at x equals 2. So the relative max is the y value at that x value. There is a relative min, let's see, and that min is 0, and that occurs at x equals 4. Now, this is where sometimes it can get a little fuzzy. So this is an absolute max. Well, it's also a relative max because it is lower than all the points in its general vicinity. So you'll see some textbooks that include the absolute max as a relative max, and then some don't. I don't have tons of clarification on this, so I'm going to state that that is also a relative min. There is another relative min, which is -8, and it occurs at x equals -3. Okay, so those are all the relative extrema. Considering the domain for G, which is all real numbers, what are the absolute extrema? Well, he only has one absolute extrema, but I'm going to communicate to them that I am acknowledging that there is no absolute max. So I'm going to write absolute max does not exist because g of x, and then I'm going to use this word, is unbounded. Is unbounded as, is unbounded, how about this? Unbounded above. So it's unbounded. It never stops. It keeps going up. However, I have an absolute min, which is -8, and that occurs at x equals -3. And that is because g of x is bounded. Now, you don't have to say that because it's implied. Okay, so process, digest, make sure you know the difference between a relative and an absolute. Okay, number 3, consider the graph just going from 0 to 12. So I'm looking at my graph, 0 to 12. Okay, well, it stops, so that's good. Find the relative extrema. Relative. Okay, so tell you what, I want you to pause it, and I want you to list what you think all the relative extrema, and then I want you to list the absolute extrema, and then hit play. All right, I have a relative max of 7 at x equals 7. I have a relative min of, let's see, the first one's going to be -2, at x equals 2, and I have a relative min of 2 at x equals 10. Again, relative extrema do not occur at endpoints. Relative extrema are on the open interval, 0 to 12. Now, absolute could happen at an endpoint. For this particular problem, it does not, but it could. My absolute max is 7 at x equals 7, and my absolute min is negative 2, and that happens at x equals 2. Okay, so I hope we've got the difference between relative and absolute and how they want it written. Okay, so now we're going to talk about the EVT. We have the MVT. We have the IVT. Now we have the EVT. The extreme value theorem. Okay, and again, this theorem is an existence theorem. It states that something is going to exist. It does not tell you how to find it. It just states that it exists. Okay, what conditions would be necessary in order to have both an absolute max and an absolute min? Okay, herein lies the EVT, which extreme value makes sense for maxes and mins. If f is continuous on a closed interval, a to b, then f has both a max and a min on the closed interval, a to b. Extreme values can occur at interior or endpoints of an interval. Okay, absolute extreme values can occur somewhere within, or it can occur on the endpoints. A function may have both a max and a min over an interval, either a max or a min, or no extrema on an interval. Let's explore some examples. And then just a little FYI, when the hypothesis or if statement is not met, either continuity or the closed interval, then there is no guarantee of the conclusion. However, a max or a min or both may still exist. The EVT just does not guarantee it. Okay, so just because this doesn't happen does not mean that this won't happen. It just means the EVT doesn't guarantee. It won't back it. It doesn't mean that it's not a true statement, but the EVT taps out. Okay. For each graph below, explicitly state where the hypothesis of the EVT fails on the interval 0 to 3. So all of these, the EVT will not touch, and I want to know why. Then determine if the function has an extrema on the interval. Okay, so EVT does not apply. EVT does not apply. Okay, why? Well, it says that we have to be continuous. We're on the interval, closed interval, 0 to 3. Because are these F? Does it label what these are? Okay, we're going to call them F. F is not continuous on the closed interval 0 to 3. However, therefore, EVT will not touch it. It will not put its stamp of approval on it. However, I, or F, has an absolute max of 4 at 1. Remember, absolutes can happen at endpoints. So we have an absolute max of 4 at x equals 1. we also have an absolute min of, we'll call that a half at x equals 0. I'm not searching for relative maxes and mins. I'm searching for absolutes. Okay, so now, how about you try B, C, and D? How about you pause me and you try B, C, and D? Okay. EVT does not apply because F is not continuous on the closed interval 0 to 3. However, oh, this is a good one. We have an absolute max of, I don't know, 4.5 at x equals 0. You do not have an absolute min. Think about it. That's an open circle. An open circle means this can get closer and closer and closer to it, but it will never, ever reach it. But I can always go farther with my decimals. So the minimum, you want to say it has a minimum of 1, and it happens at a half. But it doesn't. Number one, it doesn't ever get to 1. So what are you going to say? You're going to say it has a minimum at 1.1 or 1.01 or 1.0001. Do you see? I can always get closer to 1. So there is no absolute minimum. Okay, EVT does not apply since F is not continuous on the closed interval 0 to 3. It's not defined at 0 and it has an asymptote at 3. So same statement. Extrema doesn't have any. No extrema, no absolute max. It's got an open circle. And no absolute min because this thing will go south forever. So there is no absolute minimum. It never stops. D, the EVT does not apply since F is not continuous from closed interval 1 to 3. I have an open circle at 1. I have an open circle at 3. I could care less about the cusp. I'm not worried about it being differentiable. It is continuous on the open interval 1 to 3, but EVT says it's got to be closed. So EVT won't touch it. I have a max of 4 at x equals 1, and I have an absolute min of, let's see, does that go all the way down to -1? I don't know. It looks like more than a half. I don't know. I'm just going to say -1. Maybe like a -0.9, -0.8 at x equals 2. Okay. The extreme value theorem, EVT, gives us the knowledge of when extrema occur. But how will we find them algebraically when we're given an equation without the benefit of a graph? So our next question should be, how can we identify all the values of x where extrema values occur? Okay. For each function shown below, justify why the EVT can be applied or why it does not get applied. So right now we're not finding anything. I just want to know, does it apply or does it not? So tell you what, I want you to try these, A, B, and C. Tell me if it does apply. Here's your closed interval. So I want you to write whether it does or does not apply and why. So pause me. Okay, so for A, I have the EVT does not apply for f of x on the closed interval, -4 to 4, because it is not continuous at 2, which is in my interval, -4 to 4. For b, e to the x minus 2 is a very continuous function. If you think about the x's, think about the graph of e to the x. Even though it's shifted, it's still all the way to the left and all the way to the right. We add 1, that just jacks it up 1, does not change the domain at all. So yes, the EVT does apply because g of x is continuous on the closed interval from -5 to 5. C, no, you can't square root a negative. So x would have to be greater than or equal to a -2 for us to not be rooting negatives. And our interval goes all the way down to -6. So no, EVT does not apply because our function is only continuous for x is greater than or equal to -2, which does not apply to this function on the interval -6 to 6, the closed interval from -6 to 6. All right. So the last thing we have to talk about is a critical number or a critical value. A critical value of a function f is an x value. Okay, let's digest that. A critical value is the x value. X equals c in the domain of f such that either f prime of c equals 0. Okay, pause. F prime of c equals 0. F prime is the slope of the function at any given point. So we're saying the slope of the function is 0. That's a horizontal line. Well, the tangent line is going to be a horizontal line at tops and bottoms of humps. So a critical number or a critical value is the x value where humps happen. Okay? Or where f prime doesn't exist. And that's to include the cusps and the sharp turns. Because I can have a critical value at a sharp turn. So think about the absolute value graph. It's a V. So at that vertex, that is a minimum value. If that V opens up, that's a minimum value. However, f prime of c does not exist because I cannot differentiate at that sharp turn. So I have a critical value at tops and bottoms of humps and at also sharp turns and cusps. So where f prime of c equals 0, that covers the humps, or f prime of c does not exist. If x equals c is a critical value, then c, comma, f of c is the critical point. So if critical value, that's the x value, and then x comma y, using that x value, is the critical point. So a theorem, relative or local extrema can only occur at a critical value on an open interval. Okay, we already know that relative extrema occur on an open interval, and we already know that absolute extrema can happen at endpoints of an interval. So here's the new piece of information. Relative extrema can only occur at a critical value. Well, to find those critical values, I'm going to take my derivative and set it equal to 0, and I'm also going to think about where I can't take the derivative. Those are all the x values that are critical values. Now, for relative, that can only happen inside the interval, and for absolute, it can also happen at endpoints. So now we're going to talk about a candidate test, and this is like ridiculously important. We're going to use this like 10,000 times over the next, I don't know, month. So a candidate's test to determine an absolute extrema. Now we need to put these ideas together with a little direct practice. Let's develop an algebraic approach to what will be called the candidate's test for finding extrema. Okay, hang with me, guys. We only have 5 more examples. This is kind of where hopefully it all comes together. Find the absolute extrema of the function on the given interval, provided the EVT is applicable. If it's not, tell me why. And we see the calculator in the upper right-hand corner. That means we can use the calculator. However, we are not using the calculator to graph. If this is calculator active, it's going to be an FRQ. They are looking to see you justify using critical values. Where are you getting the critical values? And they want to see your candidates test. They're not looking for you to type this puppy into your y equals and second calc and go max and min. That's not what they're looking for. Okay, they want you to show them that you know the relationship between the calculus and finding the max and the min. Okay, so first I'm gonna say that the EVT applies because f of x is continuous on the closed interval -1 to 2. Okay. Now, I need to find my critical values. Critical values occur where the derivative equals 0. Those are tops and bottoms of humps, naturally, where maxes and mins occur. But also where your derivative does not exist, because those are sharp turns and cusps. Now, we all know that the function that's in A is a cubic function. He has no sharp turns or cusp. So I'm not dealing with the D and E's. I'm dealing with, I want to find where the derivative equals 0. So I'm going to take the derivative, and I'm going to set it equal to 0. And I'm going to factor this. I'm going to GCF a 3 just to make life simpler. There we go. And then I'm going to factor. Feel free to pause this and go at your own pace. 6 and 4, -6, +4. There we go. 3/4 and a -1/2. Okay, so those are my potential critical values. So now I'm going to do what's called a candidates test. So I'm going to make a table. And in this table, I'm going to go from endpoint to endpoint, but I'm also going to put my critical values in here. So -1, and then my next smallest number is going to be the -1/2, and then a 3/4, and then my 2. So that's from -1 to 2, because remember, absolute extrema can happen at endpoints. So I have to include the endpoints. Okay, so now what I need to do is plug these numbers into my function. Well, that's why you have the calculator. Like, they're not expecting you to type this or to do this in your head. Okay, so I'm going to save us a little bit of time, and I'm going to tell you what these decimal values are, but when you get to your homework, you need to really make sure that you practice typing this stuff in to make sure you're getting the correct decimals. You'd hate to do all the calculus right, but miss it because you don't know, I don't know, that something needs parentheses when you type it into your calculator. And once I put these numbers up here, feel free to pause it and try a couple on your calculator to make sure you're getting, especially like the fractiony ones. So the first one's going to be a 0. Second one's a 4.75, then a -3.063, and then a 36. Okay, so these, I now have the y values that occur at the endpoints, which is where extrema can happen, and at all the tops and bottoms of humps. Now, I'm looking for absolute extrema. I'm not interested in the Pilot Mountains and the Startown Mountains and the Hanging Rocks. I want the Himalayas. Like, I want the max and the min, the ultimate max and min. So, I see that my minimum, my absolute minimum, is -3.063, and it occurs at x equals 3/4. My absolute max is 36, and it occurs at x equals 2. Now, let's be super clear about some terminology, because this can really mess you up on a multiple choice question. My critical values are those two. But absolute maxes and mins can happen at critical values and at endpoints. So critical values go in the table, but endpoints also go in the table. But please do not call 2 and -1 a critical value, because they're not. Okay? All right, B. So let's see. Sine graph is like super chill, and X is linear, so this graph is super cool and no sharp turns or cusp or anything. So I'm not worried about the D&Es. I'm just worried about the derivatives. Sine. There we go. I'm going to set that equal to 0, and I'm going to get cosine of X equals subtract 1 divided by -2. All right, so then I'm going to go to my unit circle, and I'm going to find where is cosine positive pretty. So that would be pretty uglies. Pretty uglies are the ones that are far away. So pi over 3, and the one that's in the fourth quadrant, 5 pi over 3. Okay, so then I'm going to come over here, and I'm going to do my candidates test. So my x's and then f of x. Now notice I'm plugging it into the original function, not the derivative. So I have a 0, and then I have a pi over 3, a 5 pi over 3, and then a 2 pi. And then I'm going to make sure that my calculator is in radians, because I'm plugging in radian values, not degrees. So please make sure your calculator is in radians. And then I'm going to do I'm going to do 0 minus 2 times sine of 0, and then I'm going to do pi over 3 minus 2 times sine of pi over 3. I'm going to type all this stuff in, and I'm going to get these decimals. So I'm going to tell you what the decimals are, and it's up to you if you want to pause it and check 1 or 2 of them. That is up to you. Okay, so I see max, min, absolute max. Notice I don't say max, because there are two different kinds of maxes. There's an absolute max and a relative max. This is an absolute max. Absolute max is 6.968, and it occurs at x equals 5 pi over 3. And then I have an absolute min, which is -0.685, and that occurs at pi over 3. Okay, so tell you what, pause it, try C. C's got some good trig, got some good derivatives, some trig, unit circle stuff going on. So pause me and try C on your own. Okay, again, sine and cosine are super chill functions, so I'm not worried about the does not exist. This is a duck cosine. There we go. And I'm going to set that equal to 0, because the derivative is 0, horizontal tangent lines, tops and bottoms of humps. So then I'm going to GCF a sine. And then I just need to go to my circle. So sine is the y value, and that's at 0, and pi. All right, here's my interval. So I was going to put a 2 pi, but I'm only from 0 to 3 pi over 2. So that's from That's just down to south. So I don't want the 2 pi. And cosine's a negative 1/2. Again, this is my domain. So cosine to be negative would be this way. Pretty ugly. That's here and here. That's 2 pi over 3 and 4 pi over 3. Please remember, you do not get a unit circle at all on anything. So that's why we loved on that unit circle as long as we did in pre-cal. All right. Fx, start with 0. All right, now 0 checks off that and that. The next smallest one is going to be 2 pi over 3. That's him. 4 pi over 3 is over a pi. So pi goes next. Then 4 pi over 3. That's 1 1/3. And then this one is 1 1/2. There we go. Okay, again, make sure you're going to have my calculator in radians, and I'm going to do sine squared of that x value minus cosine of that x value, and I'm going to get, boy, those are pretty, but it's north, well, a lot of them are north, south, east, west. Okay, so I spy with my little I a minimum. Oh, looky there, and that happens at an endpoint. Cool. Ooh, and a tie for the max. We have a tie. Okay, so here's how we're going to write it. I'm going to do the absolute minimum is -1 at x equals 0. The absolute max, okay, watch this, is 1.25 at x equals 2 pi over 3, comma, 4 pi over 3. I share it. Okay, part D. All right, ln. Okay, now hold on. ln has some issues. ln, logs. Logs look like that. So they have issues. They are not defined for all x's. You can't log a negative number. Okay, well, what's going to make me log a negative number? Let's see. Anything bigger than a 3? No. No, I have to be bigger than a 3. 3 squared would be 9. 4 squared would be 16. That would be okay. It's anything smaller than a 3. So, well, he has stuff that's smaller than a 3. And he also can't be here. Like, he could be a -4, because -4 squared would be 16. 16 minus 9, that's cool. But he couldn't be a -2, because -2 squared would be a 4, and 4 minus 9 would be a -5. So he can't be those numbers. And there are those numbers in that number. So IVT does not apply because fx is not continuous on the closed interval -2 to 5. Woohoo. Okay, last one. Okay, this is the cube root of something squared. So this is that guy that popped up. I don't remember which homework it was, but it's been recently. And in the video I said, okay, it's the 2/3 guys that have the cusps. So he has a cusp at, I think it's at 2. Yep. It's where it's shifted is where it's going to have a cusp. And you can graph this to verify that, but it happens at 2. Okay, now, but hold on a second. Now 2 is in my interval, but again, that's cool. Like, I can have a cusp. In fact, a cusp becomes a critical value. So that just made the candidates test. Now I have to do the derivative. All right, so remember, it's this and this. And I just found this happens here because I know the mothership has a cusp at 2. So now I've got to find this one. And then all of those candidates go on the chart. So 2/3 x minus 2 to the negative 1/3 times 1, which is 2/3 cube root of x minus 2. I'm trying like that because I'm going to set it equal to 0. Now, when I set that equal to 0, I'm going to multiply both sides by what's in the denominator. Well, when that happens, everything that's in the denominator is going to go away. And when I multiply by the other side times 0, the 0 is going to eat it all. And so all I have left is the 2. I have no x's, is my point, when I solve this sucker. So since I have no x's, I get no candidates. I get no potential critical values because there are no solutions here. So I take my lone x equal 2 from where the derivative does not exist, and I plug it into my candidates test. I'm from 1 to 10, and I have an issue at 2. Like a good issue, like something interesting happens, not like a bad issue. So then I'm going to plug a 1 in here. I'm going to get a 1. Plug a 2 in. I'm going to get a 0. And plug a 10. 10 minus 2 is 8. 8 squared is 64. And the cube root of 64 is 4. So min, max. Absolute min is 0 at x equals 2. Absolute max is 4 at x equals 10. Okay. Let's take a second, shall we? Let's talk about absolute max and min. They can occur at endpoints. So that is a closed interval. Relative max and min, not at endpoints. That is an open interval, A to B. Okay. And we learned about the EVT. The EVT says if f is continuous on the closed interval, and remember that was a deal breaker for a lot of our graphs, then f has a max and min in the interval A to B. Okay. And the last thing we talked about were critical values. Critical values are where the derivative equals 0 at that value, or where the derivative does not exist. The candidates test includes critical values and endpoints, because extreme maxes and mins can happen inside the interval at those critical values or at the endpoints. So when you do your candidates test, you have your endpoint here and your endpoint here, and then all those guys go in there where the arrows are. Plug those numbers into the original function to get their y values, and then you pick the biggest and the smallest, and that's what's guaranteed by the EVT. So hopefully this page helps kind of summarize everything and wrap it up nice and put a bow on it for you.